come all the way from Colorado, where CZ has their Nunn facility, and so I know that Jeremiah knows how close I am to CZ. At any rate, I'm very grateful to be here and share your attention for the next half hour. Thank you so much for coming. I've enjoyed many of the presentations today and yesterday, and I look forward to the ones that will come after me. I'm especially looking forward to the next one, and so I don't know if everybody's met Terry Cousins, but if they look to his speaker profile, you'll see a photograph that I think is evidence that he was part of the original British invasion. So I encourage you to check into that. Anyway, what I'm here to talk about today is some work that's been done recently to try and add to the value that Coriolis meters can provide in gas measurement applications. And to do that, I'm going to go over a quick review of how Coriolis meters work, just to review the specific physics that are involved because it's pertinent later. We'll talk about AGA report number 11, which talks about some of the calibration flexibility that you have with the Coriolis meter. We'll talk about how to calculate standard volume from mass, because as many people know, Coriolis meters measure gas and liquid in mass units directly, so how can you get to the standard volume from that? And then finally, we'll get to the main heart of the subject, which is the options that are available with the Coriolis meters, and then we'll finish up with a brief discussion about verification in the field. So Coriolis meters have some very basic components, starting with vibrating flow tubes. We vibrate the flow tubes to create a rotating frame of reference, and I'll explain that some more when we talk about the physics. To keep them vibrating, there's a magnet on one tube and a coil on the other, and without touching each other, they're able to apply a sinusoidal force to keep the tubes vibrating at their natural frequency. And in similar fashion, there's a magnet and a coil attached on either side in two separate pairs to measure the vibration of the tubes. Not to be confused with the tube, the coil and the magnet that are used to vibrate the tubes. These two coil and magnet pairs are used just to measure the vibration. So when we look at the physics that are involved, what is it about a Coriolis flow meter that makes it measure mass directly? And you can see in this diagram where we've got a lumped mass model in a flow tube and a rotating frame of reference about the point P. If you imagine a rotating frame of reference with mass flowing from the center out towards the edge, you can begin to understand that to get to the edge of that rotation, the mass has to pick up some lateral velocity it didn't have before. And by the converse, when it's traveling from the outer edge in towards the center, it has rotational inertia that it has to surrender before it can reach the center. This is the essence of the Coriolis force. And I'm sure many people already understood this, but it's important to understand how we measure mass flow directly and why, what I'm going to tell you later about being able to calibrate for gas measurement with either liquid or gas is true. And it's because it's the force that's created that we're measuring. And that force can be created by molecules in any phase. And it's a similar force because it's not related to the phase of the fluid or the density of the fluid. So the way that a Coriolis meter creates this rotating frame of reference is not by rotating. By the way, if any of you were hypnotized by that, you can wake up now. This is how we achieve it without any need for seals or bearings of any sort. Just by simply oscillating the tubes a few fractions of an inch, we can create a constantly rotating frame of reference without actually having to do anything other than stretch the springiness of the tube a little bit. So how do we convert that into a measurement? Well, we have the two pickoff coils that are creating these sine waves because of their oscillating motion relative to each other, and the motion of the magnet through the coil creates a sinusoidal signal. And in the no-flow condition, as you see here, the two sine waves are in perfect synchronicity with each other. However, when you begin to flow through the meter at the same time that it's rotating because of the vibration, you get Coriolis forces that create a twisting motion. And the reason this happens is because if you think about it, on the inlet side of the meter here, the fluid is flowing from the center point P, where there's no rotation, out to the maximum point of rotation. But before it returns, it's heading back towards the center point P, where there's no rotation. It's because of the difference in this direction of motion versus this direction of motion, the you get a twisting which occurs, and therefore we have the Coriolis flow measuring in direct mass units. The only other really important point to make about this is that for gas metering, we recommend a tall tube geometry because, as you now probably appreciate if you didn't before, the fact that you have a much longer travel of that mass imparting a Coriolis force before it turns around and heads back to the center of rotation, you get a significantly greater amount of force for an equivalent mass flow rate. This is important in gas flow measurement because if you think about it compared to liquid flow measurement, it's creating less mass flow for the lower density of gas than you would with liquid at the same velocity. Make sense? Good. So this equates to greater signal to noise ratio if you create greater signal with the larger tube geometry, and that helps a lot with gas flow measurement because with a greater raw signal to work with, we're less prone to errors that are created by the secondary effects that we've heard a lot about today. So standards that are written around the gas measurement with Coriolis meters include this AGA 11 standard. There's also YML 137. But I want to specifically talk about AGA 11 because it has good directives about calibration. It was first released in 2003, and the second edition was released 10 years later in 2013. And it's also published by API as Manual of Petroleum Measurement Standards, Chapter 14.9. In the second edition, there were some important additions that were made, including a tightening of the basic tolerance. So these are the minimum performance requirements for Coriolis meters. Most Coriolis meters perform better than this in gas measurement. But it specifically mentioned that you can do water calibration and measure gas accurately as long as you've demonstrated for that particular design that transferability occurs. In most Coriolis meters, because of this relationship between the mass flow and the twisting that's created, it's usually the case. In addition, they talked about how study of the Coriolis meter by the diagnostic systems in the transmitter and the advanced diagnostics that are related to the measurement of those sine wave signals can be used as a secondary verification, much like miking an orifice plate or doing spin down tests on a turbine or a speed of sound tests on an ultrasonic meter. It's not a primary test, but it gives you a window for secondary verification, and I'll talk about that at the end. The flow testing can be performed in the field as well because of this flexibility that allows you to do testing with different fluids and draw conclusions about the accuracy of the meter. And it added some new appendices, which are also useful if you have time to read through those. So the Coriolis meters do measure mass directly, as I mentioned, and we're going to discuss now how that relates to standard volume, which is almost essential in almost every gas flow measurement application. But it does mean that because you're flowing and measuring mass directly, you don't need to know the pressure and temperature of your fluid in order to convert to standard volume. All you need to know is the base density, which comes entirely from the gas composition. The equations that are shown in the AGA standards include this one from AGA 11, which shows the very simple relationship between mass and the base density and the standard volume. So if you want to know the normal cubic meters, all you need to do is divide your mass flow measurement by the base density, which is the density at reference conditions, and it's a constant that only changes if the composition changes. Then you have your standard volume. If you were to divide mass by the actual density, which is the density at line conditions and subject to change as pressure and temperature change, then this value would be the actual volume. But most people are after the normal cubic meters. So you can skip that entirely. Here's an example where you have a flow rate of kilograms per day divided by the kilograms per cubic meter, and you end up with cubic meters per day. This next equation is identical, other than that the term in the denominator is the non-ideal gas representation of this base density. And you can note that there are many constants in here, pressure, temperature, and the gas constant. The third equation is the specific gravity, and both of these are from AGA 8. the thing to take away from this is that every term in these equations, other than the mass flow that you're measuring with the meter, is either a constant or a variable that is only dependent on composition of the gas. So everything that's circled green here changes with composition of the gas, but does not change with the pressure and temperature. This is why we say that you don't need to know the pressure and temperature of the flow rate in order to convert from mass to standard volume. So that can be quite useful if you do need to do recalculation. It makes it much simpler. All you have to do is take your previous volume measurement and multiply it by the fraction of the old specific gravity divided by the new specific gravity, or the old base density divided by the new base density, and you've got your new corrected, recalculated standard volume. Moving on to calibration, there are two things that we calibrate with Coriolis meters, just like almost every other type of flow metering device, and that's span and zero. This relationship shows the relationship between mass flow rate and phase shift being the shift between the sine waves that we measured with the pickoff coils, and it's typically a very straight line. Coriolis meters are known for being quite linear in this regard. So a line is defined by this equation, mx plus b, with b being the intercept here. Notice it's not zero exactly, and m being the slope of the line. These are used in Coriolis terminology as they're referred to as the meter zero and the flow calibration factor. And if you have variation in the meter zero, it essentially has this effect on the relationship between mass flow and the phase shift. And the thing to note about that is that the meter zero shifts really have a large impact on the percentage flow error down here in the range where there's very little flow. But as soon as you get up into this region where there's a lot of flow going on, as a percentage of flow, zero errors have a very small effect. Unlike if the flow calibration factor changes, where you have this type of effect. It's a one-for-one relationship between percentage error and the shift in the flow cal factor. So we spend a lot of time putting emphasis on getting the flow calibration factor correct, and that's what we calibrate before the meters leave the factory. This is a diagram that shows the AGA minimum standard for Coriolis meter performance. And I mentioned before, it's been reduced now in the second edition to plus or minus 0.7%. Many Coriolis meters are sold that meet a 0.25 to 0.35%, 0.5% accuracy. They fall within that range. So most Coriolis meters that are sold for gas applications fall well within this AGA 11 minimum requirement. But you'll notice that it has this range down here where we're accounting for the additional effect of zero error in the effect of how well the Coriolis meter measures below this transition flow rate, QT. Just a couple of words about that is because the Coriolis flow meters have generally better performance in this range over the wider portion of the flow range that the meter is used than the AGA 11 standard, there are two options you can use to calculate where the transition occurs. You can either base that calculation on the manufacturer's published specifications, like in this example, where we've got a published zero stability of 100 kilograms per hour, and perhaps a gas spec of 0.25%. That would mean that QT, the transition flow rate, where you cross this line, is at 40 tons per hour. However, if you wanted to have a greater extended range, you could consider QT to be defined by the point where this continuous zero stability curve actually goes outside the minimum allowable variation that AGA 11 states, plus or minus 0.7, in which case you've gotten QT down as low as 14 tons per hour with the same exact specs. Now, talking about calibration fluid and the benefit that mass flow measurement provides, in that you can calibrate the meter with water as we do in the factory and use it to measure gas. That gives you some options. You can either calibrate the meter on gas like you would, and several jurisdictions and regions and areas actually require this by law. I know Canada, Norway, and others require gas meters, even if they're Coriolis meters, to be calibrated in a gas lab. But that opens up the possibility for a new feature that we offer, which is piecewise linearization. And previously, Coriolis meters typically would have a single adjustment factor, but with this piecewise linearization, you can linearize the Coriolis flow meter over the entire flow range exactly the same way you would for an ultrasonic meter. And this is how you can add value if you're doing a gas calibration by achieving a better relative accuracy compared to your gas lab. However, because that is a relative accuracy, it will depend on the uncertainty of the lab. If you do a liquid medium calibration, there are some advantages there, and having this flexibility to choose, depending on your needs, gives you a great advantage with Coriolis meters that you can't really enjoy with any other type of meter. It is recognized by AGA report number 11 if the manufacturer demonstrates it. So you need to expect us as manufacturers to provide a document like this one here that says we did testing on this particular model and demonstrated that it was calibrated on water or any other kind of liquid and taken to several gas labs to demonstrate that the calibration doesn't shift. And that's our burden to provide that for you as the operators. But if that's available, that gives you an option for lower cost, greater safety, and speed of execution, because the meter coming to you from our factory is ready to measure. And you don't have to send it to a third-party gas lab if you have a tight schedule. So this is how the piecewise linearization is implemented. There are a couple of unique attributes to this. The ones that are somewhat intuitive are that you can collect as-found data and as many as 10 different points and create a correction curve that looks like this yellow one based on the blue as-found data. So it's just an inverse of that. The error here is corrected by an equal and opposite correction. And then in between each of the flow rates where you perform your calibration, there's a linear interpolation to connect the dots, essentially. What's different about this is if you should ever happen to flow above the maximum flow rate, where you did your piecewise linearization, it maintains the correction value of the last highest point. But more importantly, in this range here, between the lowest flow rate and 0, there's a linear interpolation that will eventually lead to 0 error. And that's not because we expect 0 error at that flow rate, but it's because you can perform an in situ 0 verification with a Coriolis meter by blocking in the meter to adjust in this range between the QT and the minimum operating flow rate much more effectively than you can by linearizing it based on a gas lab test that was done in some other location. Practices for this calibration. First, I'll begin by describing the procedure that normally occurs. It's important for the lab to install and check the meter 0 before they collect the as-found data. Then they'll want to calibrate the meter 0 if it's necessary. If the verification says the 0 is fine, which is often the case, there's no need to adjust it. After that, they want to implement pressure compensation, and I'll come back to that in a second. Before they collect the as-found data, they will then program the meter with the 10 linearization points and collect as-left data to verify that it's now measuring accurately and get a good measure of the relative error to the lab. So best practices would include paying attention to the uncertainty of the lab reference standards. You don't want to use laboratory reference standards that are not very accurate, because the meter is probably going to be accurate to within the manufacturer's published specifications on gas before you start to apply linearization. So if you use an inaccurate reference standard, you could build in error that wasn't there before. You want to make sure you check the 0, as I've said, before collecting as-found data, because if you have a bad 0 when you collect your as-found data, you're going to build that error into your linearization. You want to collect it with the pressure compensation enabled and choose up to your 10 points that you want to use, and we recommend that you do not use any points above the transition flow rate. It's also recommended that when you go back and verify after you've made your adjustments, that you select flow rates in between the as-found points to show that the interpolation is working properly. So for meter zeroing, you always want to perform that first and ensure that there's no flow, that the meter is full of your medium and there's no liquid or anything left in the meter if you do it in the field. And you want to make sure the process conditions are stable, so no temperature gradients or unstable conditions. Pressure compensation is an aspect of the Coriolis meter that I think we've discussed earlier today, but it's because of a change in the stiffness of the flow tubes that occurs when you increase the pressure inside, which makes them want to become round and also straighten out. As I think it was pointed out earlier by the gentleman from NEL, this is a very linear effect, and so it can be easily corrected if you characterize it properly. And this is shown in this data here, where you can see we have 30, 40, and 50 bar data, uncorrected, that was showing this difference at different pressures over the full flow range of the meter. However, if you recollect that data with the automatic pressure compensation using a single linear factor, it reduced all the errors to close to zero, and they're all the same for the three different pressures. Now here's the reason I bring up pressure compensation in relation to this piecewise linearization, because you have a choice if you're going to do a gas calibration to collect your as-found data with pressure compensation turned on or with pressure compensation turned off. We recommend collecting the as-found data with pressure compensation turned on, because then your linearization points are only correcting for the nonlinearity of the meter. If you were to collect it with the pressure compensation turned off, you would be building into your correction curve both that pressure compensation and the nonlinearity of the meter. And you can do that if you want by resetting the baseline pressure to the laboratory calibration pressure as your new starting point for pressure compensation, which would mean if you calibrate the meter at 800 psi, there would be no correction if you're operating at 800 psi, whereas we calibrate them on liquid somewhere below 50 psi. So just to wrap up on talking about the potential value of this, Coriolis meters are quite linear, as I mentioned, but in gas applications, there's more variation than on liquid applications. And you can see that here where we created a round-robin testing artifact by calibrating these as-found points, the blue points, linearizing the meter, and then collecting this green as-left data. We then took this same meter to 5 different labs and did a round-robin comparison without changing any of the linearization coefficients. And the thing to note from this data is that up in this range, all of it fell well within plus or minus 0.1%. So normally, it's very much expected that meters' relative accuracy after linearization, whether it's an ultrasonic meter or a Coriolis meter, will be about 0.1%, which is better than the green lines representing our water-based calibration accuracy. But what is good news about this particular data is that we can take the same meter from one lab to another lab and verify that it's not changed in terms of the linearization that occurred. So each lab re-verifies it without the need to do as-found data. This tells us that the performance in situ after it's installed and operating is also very likely to give you plus or minus 0.1% accuracy. These are just examples of other size meters where you can see the plus or minus 0.35% accuracy of these red points was reduced to well within 0.1%. And the same thing here for this 3-inch size meter. So once you've invested in your calibration, being able to verify the accuracy of the meter when it's installed and operating is the other part of AGA11 that we talked about. And this can be done by studying the vibration characteristics of the meter. It tells you about the health of the sensor, and it also performs a check on the electronics, checking the various electrical circuitry, and it also can tell you if there are conditions like two-phase flow or changing temperature in your process that would indicate that you have some process conditions which may not lend itself to the best accuracy. But the most critical part of this is the ability to measure the stiffness of these flow tubes to tell if there's been any actual physical damage that would cause the calibration to shift, like erosion or corrosion. Although it's rare, if it occurs, it will result in a calibration shift because the stiffness of those tubes is directly related to the calibration. So we do that by using 4AA analysis, where we've translated the vibration of those sine waves into a frequency response curve, and we check to make sure that the intersection of no frequency, or the stiffness of the tube, has not changed. And we can also tell if the meter's been coded by looking at whether the mass of the tube has changed. This is independent of what's going on inside the process fluid, so you can tell without having to interrupt your flow stream or know anything about your process condition, whether those tubes are still intact. So it's a very valuable tool. So to wrap up, Coriolis meters do offer many benefits that you should consider for gas flow measurement. The meters have the option for water or gas calibration if you want to measure gas. But more importantly now, if you want to measure in gas, you can achieve very good accuracy relative to the lab by doing this piecewise linearization, and our round-robin testing has demonstrated that. The Coriolis meters also can measure secondary verification methods to confirm that the tubes are still unchanged after they've been in service for quite some time, which gives you added measurement confidence in between your calibrations, so that you don't have to worry about periodic calibrations being so close together anymore. And that's my presentation. Is there any time left for questions?